This is part 5 of the combined power, heating, and cooling feasibility analysis with the RETScreen Expert software. In this video, we will further explore the capabilities of the model by looking at multiple examples. A large steam turbine cogeneration system, the use of biogas and landfill gas in cogeneration, and a ground source heat pump heating and cooling installation. Example 1, a large steam turbine cogeneration system. In the previous examples, simple reciprocating engine or gas turbine technologies were selected. Into this example, we are going to explore a more complex system, which will lead us to more options in the operating strategy section. For this demo, we will consult the built-in example available in the case studies and templates section. This could be done by clicking on the corresponding icon in the home page. In the search bar, I will type steam turbine. There are 5 examples available, 3 of them are cogeneration. I will select the one that also contains cooling. It is located in the USA. Note that this example was inspired by a real-life system. A description is available by clicking on the hyperlink. In the location sheet, I could view the climate data is the city of Rochester, located in Minnesota. In the facility sheet, a picture of the actual site has been shown. In the energy sheet, I could observe that 2 fuels were selected, natural gas and oil number 6. It looks like 2 different costs are suggested for the natural gas. Also, since the project is located in the USA, the author of the case study selected imperial units. Only one rate is selected for the electricity, which means that the electricity export rate is equal to the market rate. From the steam turbine form, I could understand that the system uses 2 high-pressure steam boilers to feed the steam turbine. One boiler is oil-fired and the other one uses natural gas. 75% of the year, the natural gas boiler is utilized. To include 2 fuels, the multiple fuel option was selected. In the steam turbine design, the extraction port option was selected. The model is then calculating the power capacity with extraction and without extraction. The heating capacity is also calculated for both cases. An extraction port is used to provide heat to a heating load at a higher grade, increasing the heat capacity of the system. However, in this situation, the power capacity will decrease. Now, let's see what operating strategy could offer in this case. There is a possibility to choose between 3 operating approaches: full capacity output, power load following, and heating load following. Taking advantage of the extraction port is also an option. However, I see that the system cannot benefit from the extraction port to provide more heating capacity. I came to that conclusion because the heat recovered column is equal for all cases. If I go back to the heating load section and increase the heating load, I will then see that both the electricity delivered to the load and heat recovered vary depending on the operating strategy because of the extraction port option. I will now click on Undo to go back to the original heating load. The heating load following shows the best operating profit and the best overall efficiency. Of course, if a better rate was offered for the electricity that could be exported to the grid, the results would have been different. Let's improve that rate. This could be done by going back into the electricity section and adding a new export rate of 25 cents per kilowatt hour, plus selecting this rate in the operating strategy section. We can now see the impact that other options are becoming more attractive. By clicking on the system design, I can now review the basics of my design, which is to follow the heating load. The steam turbine cogeneration system is going to provide 36% of the electrical energy, 90% of the heating energy, part of the heating load being an absorption chiller. Example 2, a small-scale user-defined biogas cogeneration system. In this demo, we would like to demonstrate the creation of a user-defined fuel. Also, the objective is to show how a process heating load could be considered. We will return to the case study section and type biogas to search for this particular type of fuel. I will select the 30 kilowatt biogas turbine project in the USA. From the file attached, I was able to learn that a food company is considering the installation of a CHP system in one of their farms. The recovered heat will be used to keep the digester at a proper temperature. In the location sheet, I could view the climate data for the city of Kenansville, located in North Carolina. If I click on the map and zoom in, I will be able to see the actual farm from the satellite view. In the facility sheet, a picture of the actual site has been imported. In the electricity and fuels section of the energy sheet, I could observe that biogas has been selected from the top of the drop-down list. This fuel has been created using the biogas option accessible from the options section of the ribbon. Into the biogas form, I could calculate the amount of biogas produced by the biological decomposition of various wastes. The waste generated by pigs is considered in this example. The farm maintains a quantity of 10,000 pigs and their average weight is 68 kilograms. Based on that information, the model will calculate the production of biogas and indicates the methane content as a percentage volume. Since biogas is typically composed of methane and carbon dioxide with a very little amount of other compounds, we assume that the remaining composition is carbon dioxide. The heating value of the fuel is calculated. The emission factors should be entered manually by the user. These will be used into the emission analysis. In the electricity and fuel section, the biogas rate is set to 0. The local cost of electricity is entered, and the electricity export rate is set to 0, meaning that the option of exporting the electricity to the grid is not considered for this project. In the heating load section, process heat has been selected for the type of load. First, the peak process heating load is entered. Then, the load characteristic could be defined using two methodologies. With the standard method, a constant load throughout the year is obtained. With the detailed method, the opportunity to vary the load is also given on a monthly basis. Since into the proposed case, the need for heat is higher during the winter and smaller during the summer, the detailed option was selected and the load is adjusted for each month of the year. The process load profile could be visualized into the monthly graph available into the load characteristics section, along with the power load, which is assumed constant over the year at 30 kilowatt. I assume that this does not correspond to the reality. The power load and capacity has been set to 30 kilowatt only to simplify the analysis. In the gas turbine section, a 30 kilowatt capstone turbine has been selected from the product database. It could be verified by clicking on the basket icon. The heat rate that has been proposed is quite unusual for this type of equipment. Since this number only has an impact on the fuel consumption, and my fuel is free, the financial viability will not be altered. But the emission analysis will be significantly affected. This value must be verified. By clicking on the design graph, I can now visualize my design. The gas turbine will operate at a full capacity, providing 30 kilowatt of capacity all year, except for 5% of the year when the system is not available. All the electricity will be consumed on site. The heat recovered from the turbine will provide more than 76% of the process heating load. I could verify in the system characteristics section that the remaining heat required will be provided by an existing biogas boiler. In the system summary, I could calculate the amount of biogas required on an annual basis, a little over 400,000 cubic meters, and verify if the farm could provide the required amount. Yes, the production is large enough. In the emission analysis, I could verify that this project will reduce greenhouse gas emission, no matter the heat rate of my equipment. And in the finance sheet, I could conclude that the financial viability of the CHP option is great. If I visit again the electricity and fuels section and click on the biogas option, there are two options available. We just covered biogas. By clicking on landfill gas, I get access to a completely new calculator. Landfill gas may be collected from a nearby landfill via landfill gas collection system. Let's conclude this example with a brief overview of a landfill gas project. In the case studies and templates section, I will search for landfill gas and then choose the combined heat and power example. The landfill gas form of the energy model sheet would estimate the rates of landfill gas generation over time based on the quantity of waste entered by the user. The graphs gives the potential landfill gas production rate, and the green line shows the required fuel for the proposed project. In this case, a combined cycle gas turbine could be fed with the landfill gas to produce electricity. In the emission sheet, the quantity of landfill gas consumed, flared, and emitted will be considered. Because the landfill gas emitted has a huge impact on the environment in terms of emission, most of the landfill gas example will get a very large greenhouse gas emission reduction. Example 3. Ground source heat pump heating and cooling installation. Many of the examples that we covered with the combined power heating and cooling analysis were cogeneration projects. In this example, we are going to explore a combined heating and cooling project, a ground source heat pump installation. To start a ground source heat pump project, I could click on Feasibility from the home page. In Facility, I could select Power Heating Cooling as a facility type, and then Heating and Cooling in type. Based on that selection, when I open the energy sheet, only the heating and cooling components will be shown in the ribbon and in the left menu. To complete my setup, the last step will be to open the Level 3 analysis of the cost sheet. Scroll down to the specific project cost and select Ground Heat Exchanger in the drop-down list. This extra step will allow me to size and evaluate the cost of the ground heat exchanger. I am now ready to start my analysis. For the purpose of that demo, I will instead use the Virtual Energy Analyzer to rapidly access to a built-in example. I will follow similar steps. In the VEA, I will click on Power Heating Cooling, Heating and Cooling, and a ground source heat pump analysis will be available. I propose to use Toronto for the location of the project. As for all the examples that we covered previously, step 1 consists of selecting the electricity and fuel rates. In step 2, the heating and cooling loads are estimated. The VEA suggests the heating and cooling load for the buildings based on the climate data from the location of the project, assuming a medium insulation. The software is going to present the monthly heating and cooling load profiles in the load characteristics section. A table at the bottom of this section gives a simple summary of the heating and cooling loads and heating and cooling energy requirement. In step 3, cooling equipment form, heat pump is first selected using the drop-down list. The capacity has been set equal to the peak cooling load, in this case 40 kilowatt. This value could be converted to ton of refrigeration using the unit switch. The seasonal coefficient of performance is then entered. The cooling energy delivered by the heat pump is calculated. Since the capacity of the heat pump was designed to meet the peak cooling load, the cooling delivered is also meeting the cooling energy required. The initial cost has been calculated by the VEA. This cost should include the cost of the heat pump and the cost of the vertical loop installation. We will explain later how the value was obtained. No peak cooling system is required. Similar steps were followed into the heating equipment form. We assume here that the heat pump chosen could also meet the peak heating load. Since the cost of the heat pump has been entered into the cooling equipment section, nothing is entered into that section for cost. In step 4, the system characteristics section shows a summary of this very simple system design. The system summary shows, among other information, the electricity consumption by the heat pump for both the heating and the cooling seasons. In the cost sheet, level 3 has automatically been selected by the VEA. In the cooling system subsection, a cost is entered for the heat pump only. Then, in balance of system section, using the specific project cost option, a ground heat exchanger subsection was added. By clicking on the icon, the user could open the ground heat exchanger form. The ground heat exchanger tool is used to help both size and cost the ground heat exchanger for a ground source heat pump system. 3 options are available: horizontal closed loop, vertical closed loop, and groundwater heat exchanger. To perform these calculations, some information are required: the heat pump capacity, the average load, and the site conditions. In this particular example, a vertical closed loop was chosen. The capacity were copied directly from the energy model sheet. The soil type is light rock. The climate conditions were copied from the location sheet, and the design criteria selected is cooling. The land area required for the system is calculated and must be compared with the land area available. The model calculates the ground heat exchanger pump size, quantity of circulating fluid, and pipe size. The various costs are also calculated. By clicking on OK at the bottom of the form, the main results are automatically pasted in the cost sheet. The total initial cost of the system, including the cost of the heat pump and the ground heat exchanger, could then be calculated. In this case, almost $33,000. To be consistent, the VEA takes the total initial cost calculated in the level 3 cost sheet and is pasting that cost into the energy model cooling equipment cost. For our example, the emission sheet shows a reduction of greenhouse gas emission, and the financial analysis concludes that we are looking at a cost-effective project.